Continuing along with signal propagation, we're going to take a look at some example cases here for transmission lines. So as you recall, this is the situation we're looking at. We have a Z0, which is a characteristic impedance of our transmission line, and this is the scenario we're looking at. We have some voltage source, it's going to be a step. We have a source impedance, so we label that as Z source. And what we're going to basically do is launch this basically incident wave down this transmission line, and it'll typically be reflected by the load impedance that would be sitting at the destination or load end. So initially we got a delta V0 and a delta I0 voltage and current along that line. And a little bit of time later, basically the time of flight, we're going to get a reflected wave back, which is delta V1, delta I1. And then a little bit of time later, the time of flight, we're going to get something reflected back and forth. And this will continue on until typically there's some type of steady state solution reached. So we're going to look at three different examples. This comes right out of the reference, which is the beginning of this section. I think they came there anyway. The first case we're going to look at is a large source impedance. So that would basically be the resistance associated with the FET that's driving this line. And in this case, we're looking at a scenario where it's 5 times Z0. So basically, initially when we launched that wave, it looks like a voltage divider at the input. We got the impedance of the source, and we look at the impedance down the line, and at the end of that line it's an open circuit termination. So if V in were 5 volts initially, a step, then basically the voltage that gets launched down that line is this voltage divider here, and it comes out to be 0.83 volts. So this is the voltage that's launched down the line, even though we had 5 volt on our buffer that's driving the line. So the signal will reach the end of the line after L over V seconds, where V is the velocity here, and that's basically our time of flight. I sort of said L was the T-line length and V is the wave velocity. In the case of the open circuit, the wave is totally reflected and additive. So in that case, we can calculate the voltage at the load as being equal to V incident just after L over V minus seconds. Let's say it's 0.83 volts. Now there's a new voltage at the load. It's going to be the incident as well as that reflected, and the reflected voltage is simply just the incident load times reflection coefficient. So basically that doubled. So at L divided by V plus seconds, let's say, we'd have 1.66 volts at the destination. And after 2 times the time of flight, which is 2 times L over V, there and back the wave is reflected, and that's going to be based on the reflection coefficient at the source. So as you can see, it says bouncing back and forth. And here's some of the calculations. Then when it got back to the source, we have V reflected as being the reflection coefficient of the source times the voltage that's incident, and our new voltage at the source is going to be that was initially launched, that which came back from the far end, as well as that which was reflected. And we can calculate the reflection coefficient of the source as well, because we know the source impedance and we know the characteristic impedance of the line, so it happens to be 2/3. So just working through a little bit of the details, the voltage at the source, what was there was 0.83 volts, as you recall. What's incident was 0.83 volts. It came back from the load, and then what's reflected is going to be 2/3 of that. So therefore the new voltage at the source is the sum of those, and it comes out to 2.22 volts. So it may take many L over V seconds to reach its final signal value. It's sort of shown in the figure below, and I've sort of annotated it with a couple other points of interest, like the time of flight. This is when the initial pulse reached the end of the transmission line, and then a round trip time, which is basically just 2 times the time of flight. As you can probably see, it does sort of look like an RC time constant, and that would be the behavior in this particular scenario, where the source was a fairly large impedance compared to the characteristic impedance, and it had an open circuit. And this is also why we sort of consider time of flight to see whether we need to consider it as a transmission line or not. And that was related to the rise and fall time of the buffer. Another thing that we can look at, which makes it a little bit easier to sort of understand what's going on, is to use something like a lattice diagram. It's a really straightforward representation. You may be more familiar with it like a message sequence chart. So we have time running down the page, and let's say that X could be represented along here. So this X might be from here to here, to here rather, a length of 1 centimeter. And what would happen here is we launched that first voltage wave. It traveled over to the destination. It was reflected back, traveled back to the source, reflected back, etc. And that would represent the voltages that we saw in the previous trace, where we were looking at the source voltage, or looking at the destination voltage, or we could look at it at any other point along the X if we like. This is certainly a very old representation, but it is quite useful for visualization. Second case we might look at is with a small source impedance. So Z source is quite small. Let's say it's Z0 divided by 5. Again, we have a voltage divider, the input as before, and we have an open circuit termination as before. So the initial voltage source that gets launched down that line is again just the voltage divider looking down the line, Z0 over Z source plus Z0, so it's 4.17 volts. And that's a fairly large voltage injected down that line. So the signal reaches the end after L over V seconds. That's the time of flight. And assuming we have an open circuit, the wave is totally reflected and additive. So the voltage at the load here is now 2 times V initial after L over V plus seconds, or 8.34 volts. So you can sort of see in a 5-volt technology, that's a pretty significant overshoot. So after after 2 times of flight, there and back, the wave is reflected at the source again now, and that will be based on the source reflection coefficient. And in this case, it's a negative number, which we'd again calculate by virtue of the fact that we know the source impedance and we know the characteristic impedance. So it's equal to minus 2/3. In this case, the phase is reversed, and that voltage is going to basically subtract at that end. So similar from before, we look at the reflected voltage. It's the impedance of the reflection coefficient of the source times the voltage that's incident, or voltage at the source. Now the new value is the old value, which was the 4.17, the incident, which was 4.17, which was reflected from the load, plus what is now reflected back, which is a negative number, which is minus 2.8. So we can calculate the voltage at the source now at that point in time, basically after a round trip time, as being 5.48 volts, and minus 2.8 volts are reflected back toward the load again. So this is the picture if we were looking at in terms of voltage versus time at the source and destination. And we saw here that after a time of flight, we had that relatively large overshoot, and then we had basically a large ringing on the destination. And both of these can cause some potential problems. This could cause an overvoltage, maybe damage something, and this may cause a glitch or something. So those are to be avoided, I guess, is the takeaway. Here's the third case to look at from the of transmission line. This is the scenario where we have a match source resistance Z source. So the Z source is equal to Z0, and we still have a open circuit at the far end. So again, we have a voltage divider at the input. If Vn is equal to 5 volts initially, then with that voltage divider, if these two are equal, we're going to get half the voltage launched down that transmission line. So we're going to get a wave of 2.5 volts heading from the source to the destination. Once the signal reaches the destination after the time of flight, L divided by V seconds, the open circuit reflects the voltage totally. So voltage at the load becomes 2 times that incident, or 5 volts, and 2.5 volts reflected back toward the source. But the source has a reflection coefficient of 0, so basically there's no more reflection at the source, and this would be what the timing diagram would look like. So after a round trip time, the voltage source is at 5 volts, and after a time of flight, the destination is at 5 volts. And at this point in time, we'll take a small break again and be back.